Welcome to today's lecture. Today we are going to see demodulation of amplitude modulator. Before we'll see what are all the broad classifications or techniques available in demodulation, we'll just review what are all we have seen in the last classes. In the last class we have seen double-sided band, full carrier, DSP. In short we refer it as DSP-FC. In double sideband full carrier modulation, this is our message signal M of F in terms of frequency spectrum. F, this is FM2 minus FM 0, and the amplitude is given by AM by 2 and AM by 2. The carrier signal is given by C of FF, FC 0 and minus FC, and the amplitude of carrier signal is given by AC by 2 and here AC by 2. Message signal is also referred as modulating signal. It also referred as baseband signal because we are having frequency only around the origin. Therefore, it is referred as baseband signal or low frequency signal. Our carrier signal is referred as band pass signal. Since we are having frequency only in a particular band of frequency slot, therefore it is referred as band pass signal. So our modulating signal is given by, after modulation, our low frequency carrier, according to the amplitude of low frequency signal, the instantaneous value of amplitude in the carrier signal varies. Here this is our modulated signal AC by 2 and here it is AM by 2 and here it is AM by 2. This is AC by 2, AM by 2 and here it is AM by 2. This is given by minus of FC and this is given by plus FC. So the frequency here will be FC plus FM and frequency here will be FC minus of FM, and here minus FC plus FM and minus FC minus FM. Therefore, from this, the lowest and highest frequency, we have calculated the bandwidth. Bandwidth is equal to twice the modulating frequency. This is the important parameter we have seen in the last class. So the time domain expression is given by S of t is equal to AC 1 plus Ka M of t into cos 2 pi FCT, and the frequency domain representation is given by S of F is equal to AC by 2 dou of F minus FC plus dou of F plus FC plus the second term will be Ka AC by 2 M of F minus FC plus M of F plus FC. These two are the time domain and frequency domain representation of double sideband full carrier amplitude modulated wave. And we have seen the important parameters in the double sideband full carrier amplitude modulation or in general amplitude modulation. The first one we have seen is the modulation index. Modulation index, in some books we have referred it as mu, in some books it can be mentioned it as M, but the formula for it is AM by AC. In terms of percentage, it is referred as mu percentage is equal to AM by AC into 100. This is our first term. Second term is amplitude sensitivity factor of the modulator. It is referred as Ka, which is equal to 1 by AC. And the third one is bandwidth, which we have seen just now. Bandwidth is the twice the modulating frequency. Fourth one we have seen as modulation index in terms of Vmax and then Vmin. So Vmax minus Vmin divided by Vmax plus Vmin. From the amplitude modulated wave, from the maximum and minimum value, we can obtain the modulation index. And the fifth term is power distribution. We have seen how the power is distributed in the amplitude modulated wave. It depends upon three terms. One is carrier, and the second one is lower sideband, and the third one is upper sideband. Therefore, PT is final expression for power distribution is, or total power transmitted depends upon PC 1 plus mu square divided by 2. For 100% modulation, we have identified, that is, if mu is equal to 100%, mu value is equal to 1, or PT value is equal to 1.5 into PC. And in the current distribution formula, we have seen IT is equal to IC into root of 1 plus mu square by 2. We can define modulation index in terms of power, in terms of current. Root of 2 into PT by PC minus 1. In terms of current, 2 into IT by IC the whole square minus 1. Both are in terms of power and current. And the final important one is transmission efficiency, which defines the amount of useful power in the total power transmitted. It is referred as eta. It defines the amount of useful power. So, eta is equal to mu square by 2 plus mu square. So, from this we have obtained our efficiency in DSP FC double sideband. Full carrier is only 33.33%. This is important. And we have seen the phasor representation. In the last class, we have also seen how to represent the phases of the amplitude modulated wave. AM envelope is produced as a result of amplitude modulation. We don't know how it has been created. AM envelope is produced by the vector addition of, as a result of vector addition. But what are all the components involved in the vector addition? Vector addition of lower and upper sideband. SB stands for sideband, and this vector addition again combined with resultant vector. We can name it as resultant vector. This resultant vector will combine with phase of carrier. These all three together will produce the AM envelope. So, our vector addition is VC, and this is our lower sideband, and this is our upper sideband. So, it will rotate in counterclockwise direction. Our lower sideband will rotate in clockwise direction. It is referred as VLSB, and here it is referred as VUSB. So, the resultant vector is calculated by vector addition of VLSB and USB, and this result is combined with VC. So, this will form a AM envelope. If it is in a signal, we can identify clearly. See, this is our amplitude modulated wave, and this is our V minimum, and this is our V maximum. So, our signal vector addition will be looking like this for a maximum. So, this is the vector addition, and this envelope is identified by the as a result of vector addition. If it is our V minimum value, here it will start like this. It may be in phase in some places, it may be out of phase in some places. So, this is our V max place, and this is our V minimum location. So, in V max, it will be VC plus VUSB plus VLSB. If it is our minimum location, it will be VC minus of VLSB minus VUSB. So, there is a resultant amplitude envelope, AM envelope signal is a vector addition of VC, VLSB and then VUSB. Now we will see generation of amplitude modulator, DSP FC, in particular DSP SC amplitude modulator. We have seen three methods. The first one is using a square law modulator. In a square law modulator, we have used diode or transistor in a non-linear mode. So, our message signal and the carrier signal are added together and applied to the non-linear device, that is our diode. NLD stands for non-linear device. Then the resultant is applied to the band pass filter. Here our diode is acting in a non-linear region. Here our band pass filter is centered at FC and the bandwidth must be greater than 2 FM. The resultant is our S of T amplitude modulator wave. Second, we have seen switching modulator. Here again M of T is added together with the carrier signal and it is operating in the linear region. Again our diode or a transistor which is operating in a linear region is taken for the switching modulator. The resultant is applied to the band pass filter and we are obtaining the, after filtering out the unwanted frequency, we are getting the amplitude modulator wave. Here it is operating in the, our diode is operating in a linear region, and in square law modulator our diode is operating in a non-linear region. And the third one we have seen as a product modulator. In the product modulator, our message signal M of T is first applied to a multiplier. This is a C of T. The resultant is added together with the carrier signal. If it is A, if it is B, then here the resultant will be A plus B, which will be giving the amplitude modulated wave. Multiplier can be a differential amplifier, and the gain of the differential amplifier is varied in accordance with any one of the input signals. Either it may be varied due to message signal or it may be varied according to the carrier signal. Here this adder we can use it, replace it by using an operational amplifier. So far we have seen what are all the topics which we already covered in the previous classes. Now we are going to see demodulation of amplitude modulation. Demodulation is the reverse process of generation. It is recovering the message signal from the amplitude modulated wave. There are broad classifications available. We are going to see only three topics. One is square law demodulator, the second one is envelope detector, and the third one is synchronous demodulator. We are going to see one by one. The first one we are going to see is synchronous demodulator. What is synchronous? It represents the transmission and reception should be in sync. That is, both should be in phase and in frequency. No frequency variation should be present and no phase variation should also be present. That is, that carrier which is used in the transmission side for modulation, the phase and frequency of the carrier is same in the reception side also. That is, we are going to use the same phase and same frequency which we have used in the transmission side as well as in the reception side. That is referred as synchronous detection. It is also named as coherent detection. The first we are going to see is coherent detection in the demodulation of signal. Demodulation, recovering the message signal from the modulated waveform. The first we are going to see is coherent detection. Second one is square law detector. Third one we are going to see envelope detector. First in our topic is coherent. Just now we have explained what is coherent. Coherent is transmitter and the receiver both should be in synchronous. Synchronous refers in phase and same frequency. That is, the carrier used in the transmitter side for modulation and receiver side for demodulation. Both should be in phase and it must have a same frequency. Now our input signal is S of t, which is applied to the multiplier cos 2 pi fc t. This is our resultant vector. We call it as V naught of t. It is again applied to the low pass filter to remove the high frequency components and just to pass the our message signal. The resultant will be our m dash of t, because m of t with some losses, therefore we are referring it as m dash of t. This is our coherent detector. We know the formula for S of t. S of t is equal to AC 1 plus Ka m of t cos 2 pi fct. We refer this formula as equation number 1. The second one is the resultant of V naught of t. V naught of t is the multiplication of AM modulated wave with the carrier signal. Therefore, S of t into cos 2 pi fct. We know from the equation 1, S of t is nothing but AC 1 plus Ka m of t cos 2 pi fct into cos 2 pi fct. We can replace these two terms as cos square 2 pi fct. Therefore, AC 1 plus Ka m of t cos square 2 pi fct. We know from the trigonometric identity cos square theta is equal to 1 plus cos 2 theta divided by 2. Therefore, we are replacing this with the trigonometric identity formula AC 1 plus Ka m of t 1 plus, here we have 2 pi fct, therefore cos 4 pi fct divided by 2. AC, by solving the above expression, AC Ka m of t into 1 plus cos 4 pi fct divided by 2. Therefore, multiplying this two expression AC by 2 plus AC by 2 Ka m of t plus AC by 2 cos 4 pi fct plus AC by 2 Ka m of t cos 4 pi fct. From this is our V naught of t. This signal is going to be passed through the low pass filter. This is our DC term and this is our message signal. These two represents our low frequency terms, high frequency terms. Therefore, these two terms will be attenuated by the low pass filter and only our DC term and then the second term AC by 2 Ka into m of t, which is consisting of the message signal. These two terms will be passed through the low pass filter. Therefore, the output of low pass filter is given by m dash of t is equal to AC by 2 plus AC by 2 Ka into m of t. This is the DC component which is removed by using either a capacitor or by using a primary transformer. By using a capacitor or by using a primary transformer. Our final expression for coherent detector is m dash of t is equal to AC by 2 Ka into m of t. We have seen by using the formula. By using the Fourier transform also, we can simply plot our message signal as minus Fm, and here it is F. It is referred as m of F, and the Fourier transform of the V naught of t is given by, we know the V naught of t is equal to AC by 2 plus AC by 2 Ka m of t plus AC by 2 cos 4 pi fct plus AC by 2 cos of 4 pi fct into Ka m of t. So, this is the expression we have got. So, by taking the Fourier transform, the resultant will be this will be our Ka m of t AC by 2 cos 4 pi fct term will be here 2 fc, and here it is also minus 2 fc, and this AC by 2 term is the DC term located in the origin. This is our AC by 2, and this AC by 2 Ka m of t term lies here minus Fm, and this is our cos 4 pi fct dou of f minus fc AC by 2, and here are AC by 2. If we name it as number 1, this is our first one and second. So, this is our second term, this is our third. These two represents third, and this is our fourth. M of t cos 4 pi fct set of dou of f minus 2 fc and then dou of f minus f plus 2 fc. And here our low pass filter cutoff frequency will be centered around here. Therefore, center frequency must be low pass filters center frequency is equal to 0, and then cutoff f cutoff of the low pass filter must be Fm must be less than f cutoff, and it must be greater than 2 fc minus 2 fm. Therefore, this is our f cutoff. It must be greater than fm and it must be less than 2 fc. Get the required message information signal. Therefore, these two are important for our low pass design consideration. Coherent detection, the important factor is it should not contain frequency error and phase error. For example, if we have a phase error or a frequency error, then what will happen to our coherent detection? We will see first what will happen if we have a frequency error, then we will see what will happen if we have a phase error. Frequency error in the sense we are multiplying our S of t, that is our amplitude modulated wave, with the carrier signal which is having the same frequency as used in the transmitter side. Therefore, that is cos 2 pi fct. If we have a frequency error, then it is referred as cos 2 pi f1 of t instead of fc of t, or f1 of t, which is containing either a greater frequency difference or it may contain a lesser frequency difference. Therefore, we are referring it as f1 of t. F1 is referred as fc plus or minus del f. Our del f is referred as the frequency error. It may be a larger frequency difference or it may be lesser frequency difference. Therefore, we are going to see both the cases in the frequency error. First, if we have a frequency error, assume our S of t, this is our input signal, this is our carrier. Earlier we have seen with the expression of 2 pi fc of t, now we have replaced our fc term with f1. Therefore, f1 is equal to fc plus or minus del f. This del f represents the frequency error. This is our V naught of t. This signal is passed through the low pass filter. It is given to the final expression is our recovered message signal. For example, we know that V naught of t is nothing but S of t into cos 2 pi f1 of t. Therefore, AC 1 plus Ka m of t cos 2 pi fct, and another term we have it is 2 pi f1 of t. Therefore, here from the trigonometric identity we know that cos A cos B is equal to 1 by 2 cos of A minus B plus cos A plus B. Therefore, this is for our reference. If we substitute that in this equation, AC into 1 plus Ka m of t cos 2 pi fc, we are referring this term as A and this term as B. Therefore, 1 by 2 into cos of fc minus 2 pi fc minus f1 of t plus cos of 2 pi fc plus f1 of t. Therefore, taking this term inside, AC by 2 cos of 2 pi fc minus f1 of t plus AC Ka m of t divided by 2 cos of 2 pi fc minus f1 of t plus AC by 2 cos 2 pi fc plus f1 of t plus AC Ka m of t divided by 2 cos 2 pi fc plus f1 of t. This is our resultant of our V naught of t. When we plot the frequency spectrum for del f having a larger value, then our resultant will be, this is our minus fc plus f1 value, here it is AC by 4 and here we will have the spectrum, and here we will have yet another spectrum at fc minus f1 AC by 4 and another spectrum is at this region AC Ka by 4, here it is AC by 4, again the amplitude will be, and here we have AC by 4 minus fc minus f1 and here it is fc plus f1. Therefore, at origin will have no information. Therefore, low pass filter will not obtain, cannot extract any useful information. If we have a del f value large, if del f is small, this is our first condition and this is our second condition. If our del f condition is small, the two signals together, here it will overlap. Minus fc plus f1 and fc minus f1. Here it is fc plus f1 minus fc plus f1. So, if we have a band low pass filter having a cutoff frequency lying in this region, our low pass filter will have a overlap of these two signals. Therefore, baseband spectrum will result in distorted wave. It is referred as baseband distortion. Therefore, our frequency value should not be large and should not be small. Our del f value for a coherent detection should be equal to 0. Assume if we have a phase error, we have message signal and it is multiplied by a carrier signal. Therefore, cos 2 pi fct plus theta. Now, we have introduced a phase error into the carrier signal. The resultant is V naught of t and it is applied to the low pass filter. Here high frequency components are attenuated and we will get the message signal as output. Here this theta represents the phase error. We know that V naught of t is equal to S of t cos 2 pi fct plus theta. Therefore, we know the formula for S of t, AC of 1 plus Ka m of t cos 2 pi fct. Here again it is multiplying with the factor of cos of 2 pi fct plus theta. Again cos A, cos B form, this is referred as A and this is referred as B. Therefore, cos A, cos B in trigonometric identity will be given as 1 by 2 cos A minus B plus cos A plus B. Therefore, AC of 1 plus Ka m of t will be written as 1 by 2 into cos A minus B, 2 pi fc minus of 2 pi fc minus of theta. We know from the trigonometric identity cos of minus theta is nothing but cos theta plus cos of 2 pi fc plus 2 pi fc, it is written as 4 pi fct plus theta. Therefore, when we take this inside, AC by 2 cos theta plus AC Ka m of t cos theta divided by 2 plus AC by 2 cos of 4 pi fct plus theta plus AC by 2 Ka m of t into cos of 4 pi fct plus theta. Here these two terms having higher frequency, therefore these two terms will be due to higher frequency attenuated by low pass filter. Therefore, we are end up with these two terms are V naught of t is equal to AC by 2 cos theta plus AC Ka m of t divided by 2 into cos theta. So, our output term is multiplied by a cos theta, that is attenuated by cos theta factor. I assume if we have a theta is equal to 90 degree, then what happened to our resultant AC by 2 into cos theta, that is if we substitute theta value is equal to 90 degree, cos 90 will be 0. Again here, again cos 90 will be 0. Therefore, the whole term will be 0. Our V naught of t will give, if it is referred as m dash of t. Therefore, m dash of t is equal to 0. This is referred as quadrature null effect. If we have theta value is equal to 0, m dash of t is equal to AC by 2 plus AC by 2 m Ka into m of t. This DC term is filtered by using a capacitor or by using a transformer. Therefore, this represents our coherent or synchronous detection with no frequency error or phase error. Theta is equal to 180 degree. If we take a third example, then m dash of t is equal to minus of AC by 2 minus of AC by 2 Ka m of t. Here we have an inverted signal. Therefore, inverted and in phase by 180 degree. Therefore, theta varies with amplitude. Amplitude also varies. If theta varies, then amplitude of our message signal also varies. Therefore, for a coherent detection, no phase and frequency error is the must condition. It should not occur in the coherent or synchronous detection.